Well, hello, and thank you for joining me for another Alex on Tech and ITY TV interview. I'm joined today by Steve Perlman, the founder and CEO of Artemis. Welcome to the program.
Great to be here. Thanks, Alex.
So great to have you too. Now, Steve, you have an incredible pedigree in the world of tech. You worked at Atari, you were a principal scientist at Apple Computer, you developed QuickTime, which is still used today. You invented Web TV, which lets you connect to the internet through your television set and which was sold to Microsoft for hundreds of millions of dollars. You created the OnLive gaming service, which we see spiritual descendants of in use to this day with all of the cloud gaming services. You were a division president at Microsoft and more besides, which I'll ask you to tell us a bit more about later in this interview. And now you're the founder and CEO of Artemis with this incredible P-cell technology. So let's start there. What is a P-cell? How does it work its magic? And why is it so revolutionary?
So Artemis P-cell VRAN technology is a completely new way of utilizing radio waves for communication. It achieves for real, not as a peak, but really on average, more than 10 times the capacity of the most advanced 5G systems in the world, while remaining fully compatible with existing 4G and 5G phones. And it does this by completely turning around the way that we've been doing wireless since really the beginning of wireless, which instead of avoiding interference, which is what we have with cells where they're avoiding interference between them, or with Wi-Fi where devices are taking turns in avoiding interference. Rather, the various radios that we have hooked up to the P-cell system, they all deliberately interfere. And so we create a big morass of interference. However, we do some very, very intense mathematics to calculate what is the sum of all these interfering signals at the location of each phone. And what that does, it gives many phones, as many as you'd like, the full capacity of the wireless spectrum all at once. In contrast with, say, cellular systems, you have a drop-off the further you are away from the radio tower. Mm-hmm. And there's usually only about one phone which is able to use the spectrum at once. And then all the phones have to take turns. So if you have a lot of people or a lot of data, of course, what happens is the entire thing slows down for everybody. With P-cell, everyone is able to run at near peak data rate all at once.
Yeah, well, I mean, that's completely revolutionary and completely disrupts the understanding of how wireless has worked for the last, 100 years.
It is, in a lot of ways, completely contrary. I mean, we actually, as you well know, because you wrote about us before, we announced it in 2014. And I introduced it at Columbia University. I was literally heckled.
I remember watching that video. People didn't believe it.
That's right. At Stanford University, one of the wireless professors there was heckling me. And you can see the YouTube video. Someone said, "Can we leave it to one heckle per slide?" And so, but everyone, it's hard to go and think about things so differently. We published a paper in 2015 where we explained in mathematical terms and physics terms exactly what was going on. And since then, we were surprised to see academia picked up on it. There's now more than 100 academic papers published about P-cell. It's called in academia cell-free massive MIMO, right? But many of the papers have links directly to our white paper or to our website. And this is that technology. But what we've done now and what we're announcing is, of course, that it is available. And here's exactly how it works. And here's how you'll soon be able to use it.
Yeah, I mean, I want to tell two quick stories. One was about the mid-2000s when I was at the F1 GP in Melbourne. At the time, 3G phones had been around for, a couple of years. And, I was there, would have been a Friday, wouldn't have been the actual race day. And nobody could get internet on their 3G signal. And I was the one who had the brainwave that, hey, I'll switch my phone to 2G or 2.5G as it was. And although it was as slow as a wet week, I was able to get a connection. And, funnily enough, 5G is meant to fix all the problems of congested networks and supposed to give more capacity and faster speeds. And here we are, it's 2022. I'm at the Formula One GP again in Melbourne. I'm there on a Friday again. One of the days that's not the peak race day when there's, even more people. And my phone was connected to 5G, but I wasn't getting any signal. I wasn't getting any internet. That problem of, having a full connection but nothing coming through. And it wasn't until I switched to 4G, because I remembered my experience, that suddenly, I was able to get a connection again. And so, 5G was meant to fix all these problems, and clearly it hasn't. And here we are with, with P-Cell. I mean, when I first heard about it, it sounded like tomorrow's technology available today. So, you just mentioned that it's now available, but what is today's announcement about P-Cell's new capabilities, which, leapfrog those 5G networks with 10 times more capacity, and where is it being rolled out?
So the announcement we are doing today is that here is exactly where it's available. And the first place it's deployed is at SAP Center in San Jose, California, in the arena there. We've been in closed beta. We're soon going to go now to open beta since we've announced. And people will be able to go and sign up with it by either using the SAP Center app and possibly a QR code, but it's on our website. You can see a little bit of an example of it. And the eSIM in your phone would allow you now to connect to a private network. So we're saying that P-Cell is available as a private network, not from any particular mobile operator, but rather, whoever now the customer, in this case, SAP Center, or it could be a raceway, or it could be a college campus, or a transportation hub. That's the customer who's providing you with this mobile network. And with P-Cell, you won't have the issues that you had. In fact, we are deploying this summer at a raceway in California, and after, it's going to be initially a beta test, and then after that, we'll be expanding to raceways throughout the U.S. and Canada. And we're also working with a racing franchise that is actually worldwide. So I imagine, I don't know exactly when we'll have it first available in Australia, but the technology works. It's a matter of just deploying it. It doesn't change when it crosses a national border,
Yeah. Now, one of the other things is that P-Cell allows you to get much faster throughput in smaller chunks of spectrum. So tell us a little bit about that and why that's a limiting factor for today's technologies, but not for P-Cell.
Okay, so today's technology, when you're using, let's say, 20 megahertz of spectrum, which is a common block of spectrum available for both LTE and even 5G, and in 20 megahertz of spectrum, and we clearly show this on our website, the actual achievable data rate is much less than 100 megabits per second, right? Now, that seems pretty slow compared to what we're used to, say, with Wi-Fi. Well, Wi-Fi has available about 400 megahertz, and that's why it can deliver, say, approaching a gigabit. But but if you do limit Wi-Fi to 20 megahertz, it also will be limited to less than 100 megabits per second. P-Cell, in the very same 20 megahertz of spectrum, delivers over a gigabit. And so basically, we're taking the same spectrum that's available. All we're doing is changing the waveforms going to it. And now we can deliver so much faster data rate. So that sounds like that's too good to be true. How can you have a 10 times leapfrog? That doesn't make any sense. Well, it's because we're addressing the problem a little bit differently. You may have seen ads where they show a phone that's running up to a gigabit per second, one phone.
Yeah.
But I don't think many people, in fact, it's hard to think of just about anyone who needs a gigabit per second on their phone. And in fact, their phone's going to run down its battery if it's really handling such a large amount of data all the time. Rather, the way P-Cell works is it delivers the full data rate available to each user in the 20 megahertz. So if you had, one user, maybe they're getting 50 megabits a second. But now if we have 10 users, rather than dividing by 10 to 5, instead all 10 users get 50 megabits a second. You see what I mean? So here you would have now 500 megabits a second, 50 megabits per second per user with 10 users becomes 500 megabits per second of total capacity. Now with cellular, that would never happen. If you have the ability to deliver 50 megabits a second, and then you have 10 users and divide up equally, each one gets 5. And so this multiplication of capacity is realistic because 50 megabits a second is pretty darn good if you can get that all the time to your phone. You don't need a gigabit. The thing that's an issue is when you have a lot of people sharing that capacity who then divide you down, and you find yourself below a megabit and find that you can't really uplink or downlink video, etc. So P-Cell is practical, and it addresses the problem that actually people have. It's not going to deliver 1 gigabit to one phone in 20 megahertz. Rather, it's going to deliver 1 gigabit of aggregate capacity to thousands, if a phone, hundreds, whatever number are in the area. And by the way, if you want to go to higher capacity, it can go beyond that. What we're showing today is what we have actually deployed and working right now. In 20 megahertz of spectrum at SAP Center in San Jose, we are delivering 1 gigabit of capacity, and it's completely compatible with existing phones. So it's not a theoretical thing. It's not a question of whether or not it's commercially viable.
It's working.
It's here now.
Yeah.
And that is indeed what we're deploying.
Now, as part of your new website refresh, there is a video from the chief of the SAP Center, and you're in it as well. And he's talking about how, in some seats you'd have excellent coverage, and in other seats, just a few feet away, you've got, no coverage, even though you might have the signal strength, there's just nothing happening. So just tell us a little bit about that video and about some of the other great comments that are in the press release that I will be linking this video interview into.
So Jonathan Becker is the president of the San Jose Sharks hockey team, which is at SAP Center. He's also the president of the SAP Center Arena as well. And he's a real Silicon Valley, if you will, arena owner, in the sense that he's very much interested in technology. He loves trying all sorts of new things there. And when I met with him, actually, at this point, a couple of years ago, and said, can we do testing and try? He says, absolutely. Let's go and use the arena almost like a lab and help, and gave us full access to it. And so we did that. And as we were doing the deployment, one of the things we thought would be really helpful for people to understand is to actually test the existing systems that are there, because they have a state-of-the-art cellular system for the US mobile operators, and they have a state-of-the-art Wi-Fi system. And we got 400 Android phones, which can be controlled remotely, and we spread them about the entire arena. And then we run speed tests. We're using actually iPerf on all of them at once. So boom, they all put a strain on the network. And we tested the exact same phones using cellular, using the mobile operator spectrum. Then we test them using the Wi-Fi network, and then we test them using P-Cell. Exact same phones, same amount of bandwidth, and exact same locations. And you see some stark differences. With cellular, with mobile operator, you see some seats that get almost nothing. In fact, most seats are really getting less data rate than you could use for streaming video. Other seats are getting really great service. It really depends where you're sitting. It could be actually not too far away from where you are. With Wi-Fi, it's very serious. About a quarter, 23% of the phones are told they're connected because they're very close to the Wi-Fi access point, but in fact cannot connect to the internet at all. They become sort of like a zombie phone.
It's like I was experiencing in Melbourne at the GP. I had a connection, but nothing was happening.
Yes, and what's serious about that is that there is a feature, I think, in iOS now. In fact, you explained to me a little while ago, where you can go and tell the phone, if you're not getting anything through Wi-Fi, switch back over to mobile. But that's not the typical mode. And it's not, also, I don't believe Android phones, they may or may not have that feature, I'm not sure. But the problem is, if you don't have that feature, you go into these places, you end up one of those bad seats for Wi-Fi. Your phone thinks you're connected, and then it keeps waiting and waiting and waiting for the internet to work, and you're just disconnected. In fact, I've had this happen where I leave an event, and when I get out of range of the Wi-Fi, suddenly all these messages and emails and other reminders suddenly pop coming in. Other information, because I'm finally again on the network. So and Wi-Fi, by the way, is even more erratic. I mean, the variability is just enormous. So one of the things Jonathan Becker talks about in the interview is the brand promise. The brand promise that a mobile operator, the brand promise that a venue has to the attendees that come in. And it's even more important today, post-pandemic, where we become used to being video connected. And the brand promise is that the network works. You can't have this thing where, because you happen to get the wrong seat, the network arbitrarily has poor performance, or even worse, turns your phone into a zombie phone, right? Okay, now with P-Cell gives you uniform peak performance in every seat throughout the entire arena. Full stop. It's 10 times faster than the aggregate data rate is 10 times faster than the cellular data rate in aggregate. It is 20 times faster than the Wi-Fi data rate in aggregate, for the same amount of spectrum. So it's an enormous win. And this is quite important too, because as maybe we'll talk in a minute, when we're working with private networks, typically there's a very limited amount of spectrum that's available for the private network deployment. P-cell is a spectrum multiplier. And that spectrum multiplier allows us to make private networks with the smallest bit of spectrum the highest performance networks in the world.
Absolutely. And has the public yet had a chance to try this out in the San Jose arena, or is it going to be switched on very soon?
In closed beta, so other people that agreed to keep it confidential, yes, they have used it during events. In fact, in hockey games, they're moving around very quickly in the game, in the arena. Plus, you have people milling around. But we actually even have tested it in what they call it was a Pucks and Paws Day, where people could bring their dogs. Mm-hmm. So we had hockey players, people, and dogs all moving around with, and so we now could say for certainty that even in those circumstances, P-cell works beautifully throughout the arena.
Now, you also talked about how you're using this private networks, private spectrum. So that's called CBRS. What is CBRS? What does it stand for? And is that a global thing?
CBRS stands for Citizens Band Radio Service. It's 150 megahertz of spectrum that's been recently made available only in the United States. And the way it works is, unlike the unlicensed spectrum for Wi-Fi, it's free also, but you end up reserving a spot. So with Wi-Fi, it's sort of a free-for-all, and it's very hard to predict what the performance will be. It's hard to use it in a commercial sense. With private network spectrum like this, what happens is when you ask to use the spectrum, you go to a SaaS provider, which will go and allocate you a block where it knows that there's nobody else using it, and you get to hold on to that block and use it while you need it. And so it promises to be, quite an improvement. You typically get a 20 megahertz block. You can ask for more, and maybe that's available. It depends where you are. In a rural area, you'll get all of it, all 150. If you're in a city, it's more likely you'll only get one block, right? But it's a great idea. It's not available in other parts of the world just yet, but all over the world, we're seeing the regulatory authorities allocating private network spectrum in one form or another.
And P-cell can use any of that if required.
It can, and then it also can, of course, work with mobile operator spectrum. Every P-cell unit, every P-cell deployment we do uses what we call P-Wave radios. The system is purely software defined. There is no dedicated hardware, no chips in there that are creating these waveforms. Rather, all the radio wave waveforms are created by ultra real-time software. We're using the very latest dual 64 core, 128 thread AMD CPUs that in these 1U servers. And we have developed a new type of ultra real-time virtual machine, which goes and allows us to use all those cores simultaneously with sub-microsecond synchronization. So we're able to go and use all that computing power to actually not just generate the waveforms real time, but of course do this very complicated calculation of the interference of those waveforms. And so because of that, we have the flexibility to choose any frequency we want. So yes, we work in CBRS, but suppose a mobile operator says, people in this arena are saying they've got great service in this private spectrum. I would like my customers to also get that great service. We just say, okay, here's a software configuration change. They have to give us the cryptography information, obviously, to enable their customers. Boom, that's it. The exact same deployment that we do for a private network will go and support any or all of the mobile network operators in their own spectrum. And then suddenly all of their users are elevated to this higher performance. So if you have a mobile operator and you say, I would like the performance I'm getting from this private network, tell them, because it's a simple thing for them to give it to you.
And there's no extra software or hardware required for the stadium operator. They've already got the P-cell technology installed. They just have to switch on the ability to support that carrier spectrum, and boom.
That's correct. As we add more capacity, we'll have to add more servers because there's more computation. But
that's not expensive as such.
That's correct. To deliver a gigabit of performance, it's the highest performance network, sub 6 gigahertz network in the world. Certainly the highest performance within 20 megahertz, it's 3 1U servers. That's it. There's no hardware accelerators. They're just conventional Ethernet cards, conventional RAM, and these new CPUs. When they've announced 96 core and 128 core CPUs, when those come out, we'll go down to even fewer servers. So we really are not just talking about a breakthrough in terms of the performance of wireless network. It's actually a huge breakthrough in terms of dramatically reducing the cost and complexity of mobile network deployment.
Now, most people probably aren't using their eSIM sockets. They're probably still using a physical SIM. I think in the States, some of the operators have been sort of wanting to delay people going to eSIM because it made it easy to switch to other providers. And I know that when I travel to the US, I'll get my physical SIM moved to the eSIM of my iPhone, and then I'll have a spare SIM slot to put in a local SIM card should I wish to. So what happens if I want to use PCell, but I already have my eSIM slot taken up by AT&T or Verizon or T-Mobile or whoever it is? Can I temporarily shift that and then put it back when I leave the stadium, or what happens there?
Well, okay, so you are in an unusual situation. You're a traveler coming to the United States. And the other thing is, if you have an iPhone 13, I don't know if you know, but it has 2 eSIMs. Oh, so that would be the way that is addressed.
Well, then that solves my problem. I mean, so it has 2 eSIMs plus a physical SIM slot.
That's correct. Yes.
Okay. Well, I didn't know that. There you go.
Yes. By the way, I think this is a moment in history where I may have told you something about the iPhone that you didn't know. you have educated me so much. And by the way, I hope I didn't get it wrong. But anyways, but let's set that aside. Most people have 1 eSIM. Okay. Most people in the United States, and that's of course the initial market where CBRS, we're going to get this thing going. Most people are using physical SIMs. We actually went to go and survey. We went to the different major mobile operators in the US and asked them to set up our phones with eSIMs. And it was very difficult for all of them. In fact, there's one operator, they never could figure out how to do it. We went to the store, we called them up, et cetera. So it's very new. And we're kind of relying on that in a way, because that, of course, opens up the eSIM slot for these other uses. And we know that as phones are coming, there will be more than 1 eSIM slot. Already we have an example of that. There's another thing that you should be aware of, and that is that an eSIM can hold multiple profiles. So now, we can't just go barge in if you have a mobile operator profile and add to that, okay? But we, for example, offer as one of the options for PCell, if you're let's take the example of a college campus. So the college campus would like to offer mobile service for students and faculty. So on campus, it's great. They use the CBRS spectrum, whether they're in a sports event, on campus, a classroom, in a dorm, they're getting, super high performance because PCell works so well. And then they go off campus. What happens? Well, we have roaming agreements with the national operators in the US. So the phone will automatically switch over. If it's like University of Banana, if that's the name of the university, it's UBAN, then it would still say the university as the operator as you roam around. Then and then when you come back to campus, we'll just switch back to CBRS. So we call this collective roaming. And this allows, for example, in a campus situation, maybe 9% of the time, the overall collection of users is on campus. And then we have 10% of the time somebody is going off. Well, we get billed by the megabyte when people are roaming, and we pass that back to the university. So they can look at their overall costs as being extremely low. Maybe they offer mobile service for free as a benefit to students and faculty, or they offer it at a steep discount. Meanwhile, from the point of view of the users, they have better mobile service than they've ever had in their lives while on campus. And then they have the best mobile service available for the mobile operators when they're off campus. So this is an example of having multiple profiles on the eSIM, where it has both has a profile for the private network, that is the university's name, and it has additional roaming profiles. One other example I'll just add is that there's an initial setup where you set up your eSIM. If you go to a arena for a public network, this would not have roaming for you. All of the people we spoke to who are offering public networks want to make it that they have multiple profiles so that you could go to different arenas, go to different raceways, go to transportation hubs, et cetera. Your phone's already configured. But what will show up as the operator is wherever you are. So it might say this arena, this stadium, this raceway, and then, suppose it's, a ferry, I don't know how congested things are with the ferries. I remember that I was there in Sydney, and there were times when it's very, very busy.
Yeah,
So,
absolutely.
I think that, so I think that combination of both the physical sim and then multiple profiles in eSIM will be a great solution.
Yeah, the problem is already solved, and the problem isn't something that most people are experiencing yet. But when it comes, you have a solution, and then you'll be able to rename CBRS as the Collective Bandwidth Roaming Service as well.
Oh, that's great. So, by the way, it is called the Innovation Band. That is its nickname in the United States, and we intend to make good on that name.
Absolutely, that's great. Now, you obviously don't have to have P-cell technology put into phones because it's already compatible with LTE and 5G. But
Correct.
when might we see Wi-Fi routers in the home equipped with P-cell to be a better form of mesh network, so that consumers and businesses can leapfrog the telco operators and then just start installing this technology for themselves in their own homes and offices?
So there is no inherent reason why we cannot make P-cell work with Wi-Fi. We've tested it and shown it work. The biggest problem with Wi-Fi, the biggest challenge, is that it has a long legacy. So there's a lot of devices out there that you need to test against and be compatible with. So if you're trying to launch something new, there's still a lot of devices in the mobile world, but we have a much smaller range of things that we have to make sure it works with. So after that, then I expect we will offer P-cell Wi-Fi. Then there will certainly be no zombie areas, even very high density situations. And on top of that, the spectral efficiency of Wi-Fi, particularly in high density situations, is very, very low. I mean, it's literally using this in the 400 megahertz of spectrum used at SAP Center for its Wi-Fi. The aggregate data rate is lower than what P-cell delivers in 20 megahertz of spectrum. Plus, as I mentioned, you have these other issues. For example, with Wi-Fi, there's really no good way to roam. If there's kind of an awkward sign of handover and so on. With P-cell, because we'll essentially make it so that from the point of view of the phone, it has one access point, no matter how large the coverage area. Because P-cell eliminates the concept of handover, which is what we have in cellular. You might call what happens in Wi-Fi more like fallover or whatever, because there's not like a clean handover automatically. So I think it addresses a lot of issues and will dramatically increase the spectral efficiency. And of course, you've got 400 megahertz plus of spectrum available to use. Imagine if we were getting 20 times the performance of Wi-Fi that we have today.
Look, we've all been in buildings where you bring up the list of Wi-Fi and it just goes down and down and down, and it can be difficult to get a clean signal. Sometimes you have to switch to 5 gigahertz Wi-Fi to do that, but then a lot of people know that trick. We even have the situation where you can have too many Bluetooth devices, and so your Bluetooth starts jittering and playing up. I mean, can P-cell work for Bluetooth as well?
Probably not, because I'm not sure that the protocol and the devices are.
Sure.
Are
I mean, if anybody could make it work,
enough.
Steve, it's you.
Well, the thing is, P-cell relies on feedback, relies on beacons coming back from the devices in order for it to go and figure out how to route the signal back to them and calculate the interference at the point of each device. And to my recollection, I haven't done Bluetooth LE stuff for a few years. I don't think that it has the same capability. Wi-Fi has it for sure, and so does LTE and 5G.
Now, you did mention already that more stadiums and raceways and other venues are going to be getting P-cell, I guess, rolling out over this year. And so we're going to start seeing and hearing a lot more about P-cell, which is fantastic. So what else do we need to know about Artemis, P-cell, and this news from today?
Well, so one of the things about is that P-cell is very rapidly deployable. So one of the things we're doing this summer, which is going to be fun, is we're doing outdoor music festivals. Now, those are notorious for having just no coverage and so forth. So we're going to have music festivals that have better coverage than any other place on Earth. And we can set up these things the week before. That's how fast it is to set up the technology. So that's one thing. It's kind of fun. And one of the things that you may have read some things about, I can't really, we're not allowed to announce the details of this, but I'll tell you this. You'll find it on our website. If you look at the section on, it says P-Cell MEC XR. Well, multi-axis edge computing, extended reality, what that's short for. So P-Cell, of course, will support augmented reality. You know, if you have a phone or an iPad, you point at something, the latency is ultra low, and therefore we'll be able to keep up with, you know, as you move it, and you'll be able to create, you know, an overlay of things.
Yeah.
But what's exciting is that it can do this at very high scale. So for example, if you have, you know, augmented reality glasses and you're in a cloud, in a crowd at a large festival, whether it's in an arena or at a large music festival, then it will be possible to go and augment the experience for all of those glasses at once. And the glasses will not need, you won't need to carry with you. If you want to have something that's photorealistic 3D for whatever reason, you know, maybe it's because of the festival, maybe it's because of a game you're playing, maybe it's something you're seeing in the street or whatever, you know, while you're walking around. You can have what are called MEC, multi-axis edge computing servers attached to the P-Cell servers that are ultra high performance gaming systems, or you think of them as virtual reality systems. The network connection, we developed our own Ethernet drivers, a new kind of driver, which achieves less than 20 microseconds of latency. And that allows us to go and get this feed from these servers calculating these photorealistic experiences, then get it out on the network, and then have the entire thing delivered within 1 millisecond. Okay. And that allows you to move your head around and see whatever has to be updated without, you know, you getting seasick.
Yeah.
But you don't have to haul a gaming machine on your back.
Yeah.
I mean, the CPUs and GPUs we're getting in phones and tablets are amazing.
Yeah.
But they're not amazing enough to go and deliver you the full photorealistic experience. And if they did, you'd burn through your battery and so forth.
Yeah.
That should be in the network. So we're going to see this ultra low latency multi-axis edge computing. And we really think it's going to usher in this whole new era of what the user experience is.
Yeah. As Sun Microsystems said, the network is the computer, and that's what you were doing with OnLive all those years ago. And I can think of a good reason why you want to have the crowd in the cloud with their AI glasses seeing all this photorealistic imagery. It's because you'll be able to have a drug-free psychedelic experience at a music festival.
Well, you'll be able to go and watch the band or watch a sports event. I mean, one of the things, because we're installing these raceways, so I've gotten to learn a little bit more about what the experience is there. And, you know, for a lot of the time, the cars are out of view. And I see everybody looking at their tablet or their phone to try to see what's going on.
Yeah.
Hey, how nice would it be, even if it's your phone, certainly in the early days, just to have the video work and have multiple views and everything. How nice would it be to have, discrete glasses, not something big and heavy, but something that you don't mind wearing. And have it be that you can go and immediately see the car from wherever you want. And then here's something better. What we can do is, one of the problems with us race cars is that there's not any good way to get telemetry. You might have 30 cars, say, at once on the track, and all of them
burst, right?
Well, all of them, if they want to have 4K cameras like front and back and driver or what have you, for telemetry, think about how much data you're talking about, gigabits per second, right?
Yeah.
P-Cell
from each
can
car
go and deliver. That's right.
Yeah.
P-Cell can go and handle the uplink from all these cars and have it locally routed to people in the grandstands who can choose their view. They can sit in the seat of a car while they're watching the race if that's what they want. Plus, it'll be piped to everyone at their home, and you'll have this incredible experience. I mean, it is so exciting. I mean, when I go and see these things, it's like, whoa, they're just going so fast that I can't imagine how you could possibly stay on the road. But anyways, I'm sure it's going to be a lot of fun to watch that. You can be watching a sports event and get the stats of the player. Suppose you're far away in a concert. You'll be able to go like this and zoom in.
Be right in the front row.
As if you're in the front row.
Yeah.
You know, and you'll be able to find out stuff about it. Find out about that guitar if you're into guitars. Find out, what have you. And so I think it's a great marketing opportunity. I think it's a great experiential activity. And then just like anything else, you mentioned QuickTime before. I mean, we had no idea how far, video on a computer or streaming video would ever lead to. You know, our wildest imaginations didn't come to a fraction of of where it has
What's
gone
possible
to,
today,
including
yeah.
this interview today.
Yeah.
But what this, you can think of P-Cell as one of those very fundamental enabling technologies.
I'm just thinking before about all the different angles. You know, multiple angle was sort of something that was promised for sports, and then it sort of half took off, but not really. But this is infinite angle. I mean, you can be anywhere pretty
Yes.
much. And
Yes.
you know, and look, one of the other questions I remember at the time when P-Cell was first announced, there was this hint that P-Cell could deliver wireless power. Now, I've done interviews with Ossia and Energous, and there's been lots of, you know, Motorola's showcase some things, Xiaomi, but they're all still not yet commercially available. Is this something that P-Cell can also be used for, or is that not something you're looking at anymore?
No, it can. It's something we didn't want to announce before, but it does do that. The one thing, just to set realistic expectations, it's not a phenomenal amount of power for practical, you know, typical use cases. But other use cases, it is a large amount of power. For example,
IoT devices?
I'm sorry?
IoT devices?
It depends whether people are around and what has to go through. But for example, drones that are flying around
Okay.
that need to be kept up, you know, whether it's within an event or flying around buildings in a city, maybe they're delivering things, maybe whatever it is, or providing camera views. That's a great example of where it can be used. But again, it's not the first thing we're doing. You know, you have to walk before you run, and we have to get these networks deployed. But it certainly is the case that you can, you're creating this concentration of energy where the P-Cell is, and that can be then, you know, rectified effectively. You know, it's something called a rectifying antenna or a rectenna. And then it converts it into electric power. There will come a point where you'll be able to have a phone in your pocket, and all day long it's going to be trickle charging itself. And I really think that you know, eventually we won't have to plug them in. Now, powering cars, you know, or airplanes carrying people is another story, and that we're not announcing yet.
Yeah.
But stay.
Very cool little teaser there. Now, you've been very, very generous with your time so far, and I just wanted to ask you a few more sort of personal questions before we end the interview. So, you know, in Wikipedia, it states that you built your first computer from a kit in 1976. And look, that was the time that, you know, Wozniak was building Apple Ones, and, you know, the Altair was out. And, you know, I got my first computer, the Exidy Sorcerer, in 1979. So 3 years after you, but I was only 4.5 years old at the time. You would have been a bit older. So what was that first computer? What did you do with it? And then what was your second computer?
It was a Southwest Technical Products Company, 6800. And I just happened to notice on YouTube over the last month, somebody got his hands on one, and he's been bringing it back up. And then I remember looking at it, it comes up and it shows a little asterisk. He says, looks like an asterisk with a serial port. And I'm like, yes, you got the prompt. That's what it looks like when it starts. And I'm like, I wish I could just tell him, you're there, you got it. You finally got the thing. But so that was it. And what I did with it is I started building things. First of all, I made a graphics display. So it would hook up actually through the parallel port, and then it would draw kind of brick-sized pixels on a TV screen. And I wrote video games. You know, there was one game I designed that you shoot down airplanes, they go by, and then another one that some other puzzle game. But I found I would set it up at parties, and people would. I was in high school. People would come by, and you remember that was when all there was Pong.
Yeah,
and I guess Space Invaders. And people were like, "Oh my God, this is great!" They would play. I took cassette tape boxes and put 4 buttons on them, and you could play the games. And then people would invariably, I mean, it's crazy. I'd say, don't do it. They put their drinks on the stupid computer, and someone would say, trying to save their thing, they knock it over, boom. And then I would debug it and fix it and so forth. Well, I learned a lot about how to fix computers, their inner workings, how to debug them. So maybe that, as frustrating as it was a learning experience. But anyways, I designed lots of different things to hook up to it. I designed other computers from that. Then I started, I don't know, it's funny how you get into these things. I started making all different kinds of things with 6502s, with, of course, when the 8088 came out on the PC. And for me, there's never really been a boundary between hardware, low-level code, software, high-level code, user interface, graphics. And so, you know, so it forced me to kind of have this very, very wide range where I think most of the people I know work within one field and they get very good at it. I
Mm.
ended up being a generalist, which is really great because there's some things I know pretty well, but I also am able to work with incredibly talented people and I understand what they're saying. You know, when they go and say, this is going to take this amount of time and so forth, I said, you're right. Uh, and a lot of them have had huge frustration working in companies where well-meaning people just don't understand their world.
Mm.
So that 6800 computer, whatever. I mean, it arguably that provide the basis of knowledge for a lot of what the world uses today, including the video that we're using, video streaming that we're doing right here. So anyways, next time your kid asks you for, a kit or something like that, which is something you think is something new and worthless, and they're just going to waste their time with it. Well, I don't know. I would encourage parents to always allow children to explore their passions because you never know where it's going to go.
Absolutely, absolutely. And do you remember the first time that you went online? Was it a bulletin board system or did you skip straight to the internet?
The first time I went, so there was some, we had dial-up computers, which I don't really consider the same. There's messaging between people
Yeah.
on that system, right? The first time I really would say that I was online was on the ARPANET when I went to Columbia University, which was 1979. And it was amazing because not only could you send email and I was getting like, my homework assignment for the computer science classes in email, but whoa, this is really cool. You could chat with someone at another university that was far away,
Yeah.
and
Real-time messaging.
that's
Long
right.
before iPhones and all the rest and SMS.
The other, I think I can say it now because probably the statute of limitations has gone by, but you could also get to like NORAD. They did not have very much in the way of security at the time,
Yeah.
and we were just we were looking at all the nodes and like sort of looking at the files there, and it didn't take much to get. There was a little backdoor thing, anyways. So there's lots of yeah. So I watched it evolve from being at that point universities and a few defense sites to then be more widely used by companies. And then, of course, it kind of went a different way where there's AOL, American Online, and other things like it that was a separate network for people to talk among each other. And then, of course, the real thing that kicked everything into gear was the advent of Mosaic, the invention of the web,
Yeah. And
then Netscape, and then everything else, of course, which took this thing, the internet, and created a framework and a user experience that everyone could use, and it was very, very media rich. So, anyways, but yeah, I've been connected since 1979, and I still sign my emails the way I did back then, and nothing's changed after all this time.
So how realistic was War Games with Matthew Broderick, the movie? Where he was...
I don't know. See, he was doing it later in time.
I think 83 or something. Yeah. I mean, they talked about
know.
Mr. Robot being very realistic in its portrayal of hacking, and I was thinking that that
Yes,
War Games movie must have been the early 80s version of the same sort of thing.
I think so. And
Yeah.
I was frankly surprised with how readily we could get into these systems. We had no ill intent. We were just curious and poking around, but I didn't, there's no way for us to know if something was hooked up to something. It didn't look like it. Just looked like we were getting to servers and people exchanging files and documents,
Yeah.
So I don't know, but
You were never asked, do you want to play a game?
it was never asked if we want to play a game. And as I said, if you find out shortly after the announcement that Mr. Perlman's been incarcerated, and
then we'll know. This video will serve as proof of life. Yeah.
Not have shared this information about what I did way back then.
Yeah.
But anyways, yeah.
Look,
obviously, cybersecurity is now critically important.
Yeah.
One of the things about PCell that is very interesting is that there's no known way right now to intercept the download. In other words, if you have a cellular system and you have an interception device, wherever the transmissions are, if you have the crypto keys, in theory, you can intercept what's being sent.
Mm.
Well, if you have an interception device with PCell, the points in between the points in space, other than where the user are, the data doesn't actually exist. Remember, we're creating a summation of interference signals at one point. And on top of that, you would certainly need many antennas in order to even collect the information, because the Shannon limit of what you can receive in one antenna. So that adds another layer of security to communications, which is a lot of applications. Like, for example, it could be an embassy or something where it's hard to trust the employees or maybe the government there, and you want to have secure communications to people in the embassy. So we think that there's a lot of good applications there. But one thing we mentioned on the website, you can see in the fact, is that we can't, because it's so new, this is physical layer security. We're used to security being based on cryptography, okay? Which is, of course, the application layer, but potentially could be at the lower layer, but it's not at the physical layer. This is a new thing, the idea that the signal physically cannot be intercepted, certainly for wireless. And we don't know whether there's something we've overlooked. Maybe there is a clever way to do it. We've actually asked if there are any white hat hackers out there that find a way to intercept the downlink, to please let us know. We've asked people to think of it as a layer above cryptography that makes it harder to intercept. But until this technology is better understood, do not rely on it for to say that nobody can figure it out. We just don't. At this point, it looks like there is no way to intercept it.
This could be a bad analogy, but it kind of delivers. It sounds like it delivers the benefits of quantum communication, supposedly unhackable, without quantum computers running the whole thing.
That's correct.
Yeah.
It delivers. It's a very different idea and a very different.
That's why I said it's a bad analogy.
Yeah. Like quantum communication, sometimes they call it quantum cryptography. There's no place to intercept it between the transmission and the receiver. Okay, and again, we believe that to be the case, and I'm very careful. This is important stuff, and if people rely on it, you have to always be sure. But it's going to take some years of hardening our knowledge, I think is the best way to put it. The mechanism is there. It works. We don't know any way to intercept a signal. But whether or not someone else can figure out a way remains to be seen.
Now, the next question I have, actually, I'd love to interview you on this question separately at some future time, because the question was, what are some memories you can share of your time at Apple, of Steve Jobs, of being a principal scientist at Apple, and of developing QuickTime and more? But that's probably a whole separate interview, right?
I'd be very happy to do that. It probably would run for the amount of time, but
let's skip that one and use it as a teaser for a future one. What led you to discover and then commercialize the P-cell breakthrough?
It came from the need to communicate video and virtual reality. People have gotten just lots of attention now in virtual reality, the metaverse, augmented reality, etc. Way back when, in fact, you'll see one of our early patents is about glasses with holographic lenses using virtual retinal imaging and so forth. So it's something we've been working on for a very long time. And what I quickly realized in the early aughts, the early 2000s, was that if you look at the practical spectrum that's available, the spectrum that can make it through a wall, make it through your pocket and so forth, which is what we mainly use for Wi-Fi and mobile spectrum, that pretty much is up to about 5-6 gigahertz. You go much above that, it just doesn't go through walls, and you have to have a line of sight path. Okay.
The problem exists is showcased with millimeter wave technology, which is very short range.
It's the issue with millimeter wave. The issue with millimeter wave is less about its being short range. It's just the fact it doesn't go through things. It's like light.
That's kind of what it's true.
That's right. But it ends up making short range. But that's not the bigger issue. The bigger issue is that if you hold your hand or have a case on your phone, or if your phone happens to be in your pocket or in your purse, the millimeter waves can't reach it. If someone stands up in front of you at an arena and you had a line of sight link, it goes away. So for that reason, there's a limited set of mobile applications of millimeter waves. I don't want to get into it because there's so much, there's a lot of marketing around it, and I don't want to really get in the way of that. Let me just say that from my point of view, my main interest in mobile resides in frequencies that can penetrate into pockets, hands, and so forth, and that have that flexibility. Okay, so that pretty much says you're talking about let's say 600 megahertz to 6 gigahertz. Okay. So, you're talking a fairly limited block of spectrum. Then you go and look at how many bits can be sent for a given amount of megahertz. That's called the spectral efficiency, the bits per second per hertz, or the megabits per second megahertz, and so on. And I went and calculated what was available within a local area, what can be piled together using the most advanced technologies I could find. I looked at, beamforming, MIMO. I looked at, ultra wideband. I looked at, all sorts of other, esoteric wireless technology. I actually met with people who are experts in these fields, and then I collected it up, put it into a big simulation, said, we are way short of spectrum. We're not going to have enough spectrum for the future. And this spectrum, of course, you can't create more of it because it's a physical phenomenon, right? So then I thought about, all right, if every wireless technology known on Earth is unable to increase the capacity, the spectral efficiency of spectrum, in a given local area, then we have to figure out another way. Then this is when you begin to invent. And it's another discussion about the process of invention, but it's very, very iterative. Part of the thing that is the benefit is that you become absolutely certain that conventional techniques will not work. So you explore every other thing you can think of that's non-conventional. We went through, easily over 1,000 iterations. We'd run them through, try this, try that, simulate it, think about it, and so forth. And then we arrived at, what we today call P-cell. Actually, academia calls it cell-free massive MIMO. And we went at it we attacked it from every side. This can't be as good as it is. It's too good to be true.
Yeah.
It cannot be this good. And so the simulation showed that it should work. And then we said, all right, we're going to build it. And that's what we did. We built the first prototypes. It did work. They said, well, as we scale up, it's not going to keep on scaling. There's going to be something that we missed.
Yeah.
No, it scales linearly. As we stand today, we don't know how much we can scale it up to in terms of capacity. You'll see on our website, we show a spectral efficiency graph. Whereas existing techniques like beamforming, MIMO, and so forth, they asymptotically level off as you increase the number of antennas. P-cell, as you increase the number of P-wave radios, it just gets, the capacity keeps growing linearly. So we believe that, and now we took this technology, and it took many, many years to polish it and make it so it's very practical and have it fit into the existing ecosystem. And finally, we need a little bit of help to have, new spectrum, which allows us to innovate. Without
that's CBRS.
Without the CBRS band, we would not have been able to get this product out the door, because the mobile operators are conservative, and they and their own major vendors were telling them that this would never work. So we had to go and actually get it all the way outdoor to a product where we could reach the largest customers, the mobile operators who are desperate for solving their problems, solve their problems. And now it's funny, so instead of going the front door, which would be to the mobile operators and say, hey, look, here's a great idea. We tried that and the door was slammed. Yeah. We're going to the back door, which is like, okay, we're working with your largest customers and we're delivering a 10x better experience.
Yep. And
we can get you to have that better experience in your own spectrum by just flipping a few parameters in the software. Can we now work together? And of course, nothing to announce just yet, but we are very optimistic that we'll be able to work with mobile operators and then work in their spectrum finally.
Now, normally I have a couple of questions about the next couple of years and the future, but look, everything we've spoken about is about the future being delivered today, and we can talk about this more in that upcoming interview I want to talk to you about the past and the future. But so my second last question is, what is some of the best pieces of advice? What are some of the best pieces of advice you've received in life to help you get where you are today?
I said that the number one thing I've received in life is to believe in your own convictions. The tsunami force is the only way I can describe it. The tsunami force against the conviction of making P-cell work is just unspeakable. Every quarter, everyone in industry, in academia, advice from friends not to waste your life, from investors and so forth, this tsunami force, the people who are experts in wireless, to go and say that this is not going to work. It's not practical. Okay, maybe you'll give a great demonstration, but it'll never be a product, etc. And by the way, that was the way it's been for forever.
With everything that's new. I mean, everything that's new is always laughable and ridiculous until everyone just uses it as a natural part of their life and doesn't give it a second thought.
But the thing to do though is, most of the things that I do dream up are wrong. In fact, most of the ideas we had to create P-Cell were things that didn't work.
Yeah.
So do go out there and speak to experts, hear what they have to say, listen, and if they go and point out things that don't work, then there's one or two things. Either prove that they're wrong. You may not be able to convince them they're wrong, but if you can prove to yourself that they're wrong, fine. If not, adapt. Take that and take it as a learning experience. So this doesn't mean just go plow along. You're always right. That's not it at all. You're usually wrong. I am usually wrong. Okay. It's when you finally have honed into something and the world still tells you that everything you're doing is wrong and you're tilting at windmills. Then just stick with it. It makes life worth living. It's how change happens. It's how we move forward. And so anyways, I'd say that by far is the biggest advice I could give anybody. Just believe in your own convictions, prove them, convince yourself, and if nobody else believes them, stick to them.
Excellent advice. And so my final question for today is, what is your final message to IT Wire viewers and readers, to the industry at large, and to your current and future customers and partners?
I guess my final message is that we believe that we're opening a door to a fantastic new future. We are looking to partner with everyone. We're looking to partner with other vendors, with operators. We're looking to partner with our end users. You are the ones who are going to come up with the creative ideas. We're creating an enabling technology. We're creating a platform that is immensely powerful, that we haven't begun to dream up the things it can be used for. And our arms are open to try to work with you and see what we can do to invent the future. So I'm very, very much looking forward to every day going forward from this point.
Well, Steve Pearlman, it sounds like you've created a stable wormhole to the future. All we're going to do is step through the Stargate, and we're there, right? So it's been very exciting to learn about P-Cell from its founding a few years ago to today's news of the stadium deployment and future deployments to come. So I really look forward to learning more about it. I wish you the best of success. I look forward to our next interview, and thank you very much for your time.
All right, thank you. Great talking to you, Alex. Bye-bye.
Talk again. Bye-bye.